My name is Taylor Hill. I am a senior in the Industrial Technology program at the University of Idaho. This is my Capstone 1 project. This is our $100 ultrasonic generator. We built this using components from an ultrasonic bath off the shelf that we purchased, and we put the usable components into this control box. We disabled the heating circuit that was originally used in the ultrasonic bath and just kept the ultrasonics. Essentially what this box does is it takes a 120 volt 60 hertz AC current and it transforms it into a 250 volt 20 kilohertz pulse width modulated DC. The DC output is transferred to the transducer. This is our piezoelectric transducer. It's composed of two piezoelectric discs that are sandwiching an electrode. What happens is the high frequency current gets pushed into the electrode where it's forced through the discs to find ground. The discs expand and contract at the frequency of the voltage, so in this case 20 kilohertz. Those vibrations are then transferred through this aluminum horn into the vessel and into the fluids which are contained in the vessel. Now we can turn it on. The only adjustment that we have on this unit is for time. We can set the time that the ultrasonics will run for up to 30 minutes without damaging our components. So you can see from the video that the sound waves are traveling through the water. At this volume of water, we do have some sound waves that are escaping into the air through the fluid gas interface, meaning that we could still put more fluid in it and run it to full efficiency. The main benefit to running high frequency sound waves through fluid is the formation of cavitation bubbles in the fluid. As the waves move through the fluid, they create tiny little vacuum bubbles, which almost immediately implode on themselves, which causes a type of turbulent scrubbing action. It makes them very useful for cleaning and also for assisting in chemical reactions.
My name is Ethan Struess. I'm a PhD student in the College of Mechanical Engineering here at the University of Idaho. And we hope to be able to apply this technology that Taylor described for the use in our pyrolysis unit. This transducer is not able to withstand high temperatures, and so we will apply it in our cooling unit. This right here, we are going to use as a quenching column, where we will use have a reservoir of quenching fluid located at the bottom, where it will be subject to ultrasonic waves. And as the high temperature vapors enter and mix with the cold quenching fluid, the ultrasound will help induce mixing, and the hope is that it will increase our oil yield and quality. In the future, Taylor will touch on that a little bit, but we also hope to be able to develop a higher temperature ultrasound unit, which we can directly apply to a slow pyrolysis unit that we will be using to break apart plastics in solvent and perform solvent liquefaction in there. And the ultrasound will help in those chemical reactions as well as in the physical mixing.
So next steps, like Ethan mentioned, one of the biggest limiting factors for using this type of technology is temperature. Piezoelectric transducers are very temperature sensitive, and they'll break down their crystalline structure, some as low as 50 degrees C, so they're not great for high temperature application. So in order to overcome this, we'll try to develop a new interface which will allow us to thermally insulate the transducer while still being able to conduct the sound waves through it. This interface will have to be also electrically insulating as well, as the piezoelectric transducer is energized, and so will energize whatever it's attached to. So it can become kind of tricky to be thermally and electrically insulating while acoustically transmissive, and that will be one of our goals in upcoming projects, as well as scaling up the generator to higher output, potentially a generator that has adjustable frequency, so we can also experiment with using different ultrasonic frequencies and their effects on the pyrolysis units.